All right, number 5. This one's going to be a lot simpler than you think. Write the electron configuration for the following. Sodium. Okay, I can do that. I can write 1s2, 2s2, 2p6, and then 3s1. We can do that. Easy peasy. We did that a while back, as a matter of fact. But when we go to B, we see sodium with this little plus mark up here. That's indicating the positively charged sodium ion. Now, in order to get a +1 charge, that means that we have jettisoned, we've removed 1 electron. Now, out of all of these electrons here, the one that is most likely to be lost is this one. The highest energy electron. That's the one that's most likely to be lost. And so, we're losing 1 electron. It's that one. So when we go to write the electron configuration of sodium +1, we're going to include all these same electrons except for our 1 3s electron. So we'll go 1s2, 2s2, 2p6, and stop there. Now, 2 things I want to point out. The only thing I did was drop this 3s1 electron, but I also want to point out that I have a full octet in n equals 2. In the second row, I have a full s and a full p sublevel, combining for 8 valence electrons, right? Valence electrons, the s and the p sublevel. There's 8 right there. That's a noble gas configuration. That's a noble gas configuration of neon. That's nice and stable, right? Noble gas electron configuration. Let's do the same thing for oxygen. We're going to just write the regular old neutral form of oxygen. We're going to go 1s2, 2s2, 2p4. 2p4. Now, oxygen as a -2, as a negatively charged ion, is going to be gaining 2 electrons. That's why it has a -2. It has added 2 negatively charged things, right, electrons, to have this negative charge. So we are going to add 2 electrons to this 2p sublevel, and that will actually fill up this 2p sublevel. So for the +2 form of oxygen, we'll go 1s2, 2s2, 2p6. All right, this is where we put those 2 extra electrons that we just gained. But guess what? This is a full p and s sublevel. 2 plus 6 is 8. This is my satisfied octet rule. I have 8 valence electrons. Noble gas stability, that noble gas is neon. It's actually the same noble gas configuration that the sodium ion obtains. Okay, it's just that this atom right here, this ion, is accomplishing that by gaining 2 electrons. So the sodium ion is accomplishing this by ditching 1 electron. But both end up with the exact same electron configuration as neon. Now let's just do one more. Let's just cut straight to the ion here for cobalt +2. So we're going to look at cobalt, and it's a +2 charge. And so whatever our normal configuration for cobalt is going to be, we're simply going to take away 2 electrons, right? Not that complicated. Not that complicated. So here we go. 1s2, 2s2, 2p6. Now we're going to get into some action that we're going to start counting some stuff here. So we got neon, then we go 3s2, 3p6, and then we go 3d7. Now you might think, wait a minute, shouldn't it be 4s2, 3d7? Because wouldn't we take away those 3d electrons? And that's a very good idea. And most of the time, that's exactly what would happen. But cobalt is in these transition metal, the D block elements, and it doesn't always follow the rules. There are exceptions or irregularities within the D block. That's why I'm not going to ask you very many questions about them, because there's a lot of exceptions to the rules. We want to focus on the rules here. And so it turns out the 2 electrons that were ejected from the cobalt atom when it was neutral to make it this 2+ form, the 2 electrons that were booted were actually the 4s electrons. There would have been 2 4s electrons. Those were the 2 that were booted to make this +2 form of cobalt.